Hi professors and everyone, my name is Iyo. I'm excited to share with you my work on universal adversarial network attacks on autonomous vehicles. Autonomous vehicles have gained rapid commercialization today. Using Baidu Apollo Go as an example, it has launched its robotaxi service in various cities in China, such as Wuzhen and Beijing. Allow me to share with you a short video from Baidu on how it works. With this trend of rapid commercialization and increasing regulations, the importance of safety in autonomous driving systems, or ADS, are becoming more significant today. Therefore, the objective of this study would be to study the safety of autonomous vehicles. This study focuses on the traffic light recognition system of Apollo ADS against the Universal Adversarial Network Attack, or UAN. This consists of three parts: setting up the Apollo ADS testbed environment for this study, the effectiveness of the UAN attack on the traffic light recognition model within Apollo, and whether such UAN attacks can be implemented feasibly by the attackers. The first part of Apollo ADS testbed environment consists of both Apollo ADS and LGSVR simulator. The Apollo ADS is an open source meant to accelerate development, testing, and deployment of autonomous vehicles. The second part will be the LGSVR simulator. LGSVR simulator is an open source end-to-end simulation platform to test and verify autonomous vehicles. This will be how our LGSVR simulator functions. This is the LGSVR simulator. We observe that the LGSVR provides a realistic environment for the autonomous vehicle. Hence, the traffic light from the LGSVR simulation is passed as an image into Apollo via Apollo's cameras. This will be how the Apollo ADS perceives the environment, such as the traffic lights. Therefore, the traffic light image is being classified by Apollo's ADS traffic light recognition model to give a color of the traffic light. The output of the traffic light recognition model can be seen separately with a cyber monitor. Currently, it is displaying a color of red with a confidence of 100%. We confirm this with the LGSVR simulation, and indeed, it is also representing the same color classification. One functionality also includes giving the autonomous vehicle a pre-planned route. This is done using Apollo's ADS, setting the final destination of the vehicle.
Entering to
We
auto
observe
mode.
how Apollo is able to drive itself autonomously through this route and classifies the traffic lights correctly within both the Apollo ADS as well as the LGSVR environment. Here we see a red light, and recognizing that it is red, the Apollo ADS vehicle remains stationary and wait for the traffic light to turn green. Upon turning green, Apollo vehicle was able to classify it correctly and cross the traffic light safely to reach the final destination. The second part would be to build a UAN attack against Apollo's traffic light recognition system. UAN is built upon Universal Adversarial Perturbations, or UAP. UAP is defined as a single perturbation, when applied to any input, will cause a misclassification with high likelihood. By learning to build UAPs on image datasets, generative models will create a UAN attack. It is a black box adversarial attack, where adversaries have no knowledge of the model behind the ADS. It is also a universal attack, resulting in misclassifications given any input. This is an example of how UAN disrupts the original image, giving an adversarial image. The original truth classification is green. After the UAN attack, it is misclassified as black. Variations of the UAN attack can be made by varying the maximum allowed perturbation from 0.15 to 0.5. The UAN attack is then carried out on different traffic light colors. We can observe that the higher the amount of maximum perturbation, the more perceivable it is for humans to tell that it is attacked. The results are as such. The UAN attack is used for both the surrogate DensNet model it was trained on, as well as the traffic light recognition model of Apollo, the CAFE model. As the size of perturbation of UAN increases, the success rate of attack increases. For the surrogate DensNet model, it is able to achieve a 88.6% success rate of attack and 34.4% for the CAFE model. Therefore, the results of the UAN attack shows that it is effective in fooling the CAFE model, resulting in wrong traffic light colors being classified by Apollo. In implementation, we insert the UAN attack into the traffic light recognition module of Apollo in runtime environment. After analyzing the pipeline within Apollo, we decided to insert the UAN attack into the perception model before it is being passed into the recognizer or the cafe model. Using the image of the traffic light with the bounding boxes, we'll be able to insert the UAN over the original traffic light, thus implementing the UAN attack. Let us now visualize this UAN attack in the Apollo runtime environment. Despite best efforts to insert the UAN attack, Apollo was still able to perceive the traffic lights correctly. From the output of the Cyber Monitor and LGSVR simulation, we see the traffic light color green corresponds to the simulation's green. This was also correct for yellow as well as red. This was also confirmed by observing how the autonomous vehicle was still able to cross the traffic light after we give it a planned road.
Entering to auto mode.
It recognizes that it is a red light, so it stops within the ADS, as well as within the LGSVR simulation environment. There are various defenses that may explain why it was difficult to implement a UAN attack in the runtime environment. Firstly, there were defenses to prevent reverse engineering, such as redirecting outputs during runtime to prevent debugging. Secondly, there were also defenses outside of the traffic light recognition model. Even if the UAN attack worked on the cafe model to misclassify the traffic lights, Apollo may have applied some heuristics to correct the results. This exists in the form of sequence constraint and time constraint. Therefore, even if UAN is able to attack the cafe model successfully, there are still other defenses of Apollo that prevents the eventual misclassification in runtime environment. Hence, Apollo ADS, as a whole, is robust enough to defend against UAN. Considering how Apollo has received regulatory approvals, passed trials, and reached commercialization, this puts our minds to ease. With that, we have come to the end of our presentation. Thank you.